Hello, everybody. I'm Felix Neutatz, and today I'm excited to share our work on declarative feature selection. And this is joint work with Felix Biesmann and Siavash Abedian. Nowadays, machine learning is not only about model accuracy anymore. There are many more dimensions. One example is Netflix. Netflix had a competition on finding the best possible recommendation algorithm, but they were not able to actually deploy this algorithm because of engineering costs and therefore deployment constraints. Another example is Amazon. Amazon had an AI recruiting tool, but it was discriminating against women. So another important requirement or constraint is fairness. And third, Microsoft deployed an AI chatbot, which was fed bad data from some adversaries. So the third example is an example for safety constraints. Safety is important. One way to enforce these constraints is to enforce these constraints in a machine learning model. And here we have two examples. So you can enforce fairness and differential privacy constraints by adjusting the model objectives or the model architecture. The problems with this approach is that it requires ML expertise to design these architectures and objectives according to the constraints. And whenever there's a new constraint upcoming, we might need to redesign the model architecture or the objective from scratch. Instead of enforcing the constraints in the model, we were asking ourselves, can we also enforce these constraints in the data? And more specifically, we looked into feature selection. So here in these two charts, you see each point corresponding to one feature subset of the COMPAS dataset. The COMPAS dataset is a well-known dataset in fairness literature, which contains records of offenders and whether they will relapse before trial or not. So if we now look at these different feature subsets according to different metrics, more specifically F1 score and empirical robustness against adversarial examples, and on the other hand, F1 score and equal opportunity, which is a fairness score, we can now look at the original feature set. So here you can see it has a relatively low empirical robustness and also rather low equal opportunity. So by adding and removing features, we can both increase the empirical robustness and also the equal opportunity. So by this, we showed that indeed we can leverage feature selection to address a large number of ML application constraints. It would be great if we could specify the problem of feature selection in a declarative way. So the user would specify the constraints, for example, fairness and adversarial robustness, and our system would find the features that satisfy all these constraints. And the big advantage of this approach is that we do not require ML expertise, and we can also simultaneously satisfy multiple constraints. But now the question is, which is the right feature selection strategy to actually achieve this goal? And as you can see here, there's a large number of feature selection strategies. For example, we have multi-objective and single-objective strategies. For multi-objective approaches, one example would be the evolutionary algorithm NSGA2, while single-objective approaches are more common. So, for example, we can evaluate all possible combinations of features in an exhaustive manner. However, for a large number of features, this is not a viable approach. Then there's sequential feature selection, where we start either with the empty or the full feature set and then incrementally add or remove features. And finally, there's randomized approaches, for example, ranking strategies that are based on similarity, information theory, sparse learning, or statistics, or without ranking would be an example of simulated annealing. So having all these strategies, the question is, which one should we actually choose? And there are trade-offs between these strategies. For example, ranking feature selection strategies are fast because of their complexity of ON, where N is the number of features, but they mostly do not work well with many complex constraints, such as fairness. While sequential feature selection strategies are rather slow because of their complexity of O(n squared), but they fit well for multiple constraints and also complex constraints such as fairness. To this end, we make the following contribution. We analyze which feature selection strategies are suitable in which cases across novel ML application constraints, and we propose a DFS optimizer that can choose the feature selection strategy that is most likely to satisfy the given scenario. And in order to make these contributions, we propose the following declarative feature selection workflow. As input, we get the features, for example, education, gender, experience, and race. Then the classification targets, should we hire this applicant or not? Some application constraints. Then we split the data into training, validation, and test. We have a ML model and some ML model hyperparameters. In the next step, we provide this input to the DFS optimizer, and then magically, I will describe later how exactly, the DFS optimizer proposes a feature selection strategy, which then proposes some feature subset, which we use then to train the machine learning model using the training data. And we will optimize the model parameters on the validation set based on accuracy. And finally, we will evaluate all the constraints again on the validation set. And here, for single objective approaches, we will measure the distance to satisfying all the different constraints that were satisfied. And this distance we will then again provide back to the feature selection strategy, which will then again propose a new feature subset. And in the end, we will get a feature set that satisfy all the constraints on the validation data. And we will verify whether that's also the case in the test data. And finally, if that's the case, we will get the features that satisfied all our user constraints. The challenges of this approach are that feature selection is known to be hard, in fact, NP hard, and picking a successful feature selection strategies from the multitude of strategies is also extremely hard. To achieve our vision of declarative feature selection, we first looked into ML application constraints, and more specifically, what constraints happen in day-to-day ML applications. And these constraints differ in their characteristics. Some of them are evaluation dependent, meaning we require model training, for example, minimum accuracy. Some of them are not. For the maximum feature set size, we do not need to train a model to verify whether this constraint is satisfied. Another characteristic is the dependence to the number of features. So we saw that more features are usually beneficial for minimum accuracy constraints, while less features are usually beneficial for minimum privacy because the likelihood that data is leaked is lower. And finally, they also differ in their required inputs. So again, for the maximum feature set size constraint, we only require the features in order to understand whether the constraint is satisfied or not. Now that we understand the ML application constraints, the question is, how can we actually design a DFS optimizer that can map an ML scenario to a feature selection strategy that can satisfy all the constraints? So in order to make the decision to choose the right feature selection strategy, we need the main components of the ML scenario. And these are the following. We need the data set. For example, before we already saw that the data set shape has an impact on the feature selection strategy complexity. Then we have the ML model. Here, one example is that some models have the assumption of feature independence, and depending on whether the feature selection strategy have the same assumption, they work well together or not. And finally, we have the constraints themselves. And like I said before, If we have multiple constraints, that might be an issue for some of the strategies that are not as flexible. But we also have some requirements for this DFS optimizer. First, we do not allow trial and error because we do not want to run multiple feature selection strategy and then know the results. We want to be fast. So trial and error is not allowed. Secondly, we require extensibility to more constraints and strategies. And related to this requirement, we require no human supervision because whenever there's new constraints or strategies added, there should be no human that has to label or add any rules to the system. Based on these requirements, we have to specify the problem as a classification task. So again, we have as the input the ML scenario, namely the data set, the ML model, and the constraints. And based on this scenario, we will predict whether a given strategy will satisfy the scenario or not. So for each strategy, we have one ML model that predicts the likelihood of satisfying the constraints. And then we can just pick the strategy that yields the highest estimated likelihood. So in this case, strategy 3. Now you might wonder, how do we actually get the training data to train all these classification models? Here, our approach is to first specify a template for the search space. So the search space based on the classifier, the constraints, such as, for example, maximum search time between 10 seconds and 3 hours. And we will sample from this space and then execute all the feature selection strategies, which yields us the training set we need. So now the question is, how can we actually featureize our ML scenario? For the data set, we can take the number of rows and columns. For the ML model, we want to hot encode all available models. And for the constraints, we take the thresholds here, 80 and 95%, and we apply landmarking. Why we need landmarking, I will discuss in a moment. But the good thing about these features is that they provide extensibility to more models and constraints. So if we have another model, we can simply add one hot encoding feature. Or if we have more constraints, we can add more threshold or landmarking features. To choose the right feature selection strategy, our DFS optimizer has to understand how restrictive certain constraints actually are. So here we have an example of some user constraints where the fairness is greater 90% and accuracy is greater 80%. So for a linearly separable data set, an accuracy of greater 80% would be an easy task to achieve. Whereas we have more complex classification tasks, this might be actually really hard to achieve. So it really depends on the data set whether these constraints are restrictive or not. And in order to understand how restrictive they actually are, we leverage landmarking. So more specifically, we take a small sample of the data sets, then we apply a fast model, here logistic regression, and we get the corresponding scores on this very small sample. So here fairness of 80% and accuracy of 90%. So we can actually clearly see already that the accuracy constraint is not the problem here. We already achieve very good accuracy on the small sample, while the difference to the fairness constraint is higher. It's around 10%. So here, the fairness constraint is more restrictive. So it turns out that landmarking is a fast and effective way to estimate the difficulty of satisfying the constraints. To evaluate our optimizer, we designed a benchmark, which consists out of 3,318 scenarios, a 19 data set, 6 ML application constraints, 3 classification models, and 16 feature selection strategies. And the data sets vary across instances, attributes, and features, and also the corresponding sensitive attribute, which we use for fairness. The research questions that we answer in these benchmarks are the following. which strategy can cover most scenarios and which strategy is the fastest? Can we learn to choose the best strategy using our DFS optimizer? Can we combine multiple strategies and be effective? And other questions are, how is the strategy performance affected by different ML models, dataset, and constraints? And which strategy is actually best if we optimize a utility? And finally, can we reuse features for other models? The bold questions I will answer in this talk, while the other ones I would point you to the paper. And these are some results. So here we look at two metrics, fastest and coverage. Fastest is the fraction of scenarios that a strategy X was the fastest, and coverage is the fraction of scenarios that a strategy satisfied. As we can see, none of the strategies are always the fastest, and none of the strategies can cover 100% of the scenarios. The second thing we can see is that indeed our DFS optimizer reaches a 10% higher coverage than any single strategy, in this case, a tree-Parson estimator with ranking or fast correlation-based filtering. But we also see that there's still a lot space for improvement to achieve the theoretically optimum of 100% of the scenarios. Instead of running just a single strategy, one could also run multiple strategies simultaneously. And we did exactly that. And we looked at which of the combinations yield the optimal coverage or the optimal speed. So for example, here, tree-Parson estimator with fast correlation-based filtering as ranking, together with sequential floating forward selection, yields already 83% coverage. That's really good. And the same is true for speed. So if we just run 5 strategies simultaneously, we already get, in 52% of the cases, the fastest result. And in this implementation, we do not yet leverage any synergy effects that could be leveraged, but we already see this really good number. So there's still potential for future research to close this gap. So to conclude, running complementary strategies is highly effective. To conclude, we propose declarative feature selection, which allows a user to specify multiple diverse ML application constraints that are then satisfied by feature selection. And we proposed an optimizer that leverages meta-learning to choose the feature selection strategy that most likely satisfies the user's constraints. And you can find the code openly available on GitHub. And with that, I would like to thank you for your attention and goodbye.